Hi, welcome to the second unit of bioprocess technology. It's about industrial strains. Strains are basically different varieties of a same species. Whether it is a microorganism, whether it is a plant or animal, there are different varieties within a species. All these varieties are belong to a single species, but they are different. For example, in case of mangoes, all mangoes belongs to a same species, but there are different varieties of mangoes. They differ in their shape, in their color, in their flavor. So these are the different varieties of mangoes. In case of dogs, we know there are different varieties of dogs. All of them belongs to a single species. Even for the humans, we have different varieties or different races of humans. There are Africans, Americans, Asians. They are different, but they belong to a same species. So in this unit, we are going to talk about industrial strains. So the microbial strains are the genetic variants or subtypes of a microorganism. Within a species, they classify it as a subtype or a variant. If I pull out one example, we had coronavirus. It has four different strains: the alpha, beta, gamma, and delta. They all belongs to the coronavirus, but they differ slightly in their core protein structure. Now we have the novel coronavirus, which is different from all the four existing strains. It's new one. It's more pathogenic. So it's a strain of coronavirus. It already have four different strains. Now we have a new one. So now it comes to five different strains. In industry, even if we are using a particular species of microorganism, based on the process, we may select one variant or another. The most widely used microorganism in the industrial biotechnology will be the Saccharomyces cerevisiae. We know it can be used for baking industry, for breweries, as a probiotic, everything, but it is not the same organism. Of course, we are using the same species, the Saccharomyces cerevisiae, but the different variants are used in different purposes. For example, the Saccharomyces cerevisiae var ellipsoides, var stands for variety. It's Saccharomyces cerevisiae, the variety called ellipsoides, is used for wine making. Another variety, Saccharomyces cerevisiae var diastaticus, it is a beer spoiler. So one variant is an excellent winemaker. The another variant of the same species act as a beer spoiler. Further, Saccharomyces cerevisiae var boulardii is a probiotic. It is used as a medicine. So within a species we have different variants. Different variants may have different industrial applications. If we look further, we can see that all different wines are not same. There are wide variety of wines. They are sweet wine, sour wine, they have hard wine, light wine. This one of the reasons for different categories of different types of wine, they are using further super variants for each category. So the variants, the ellipsoides can be further divided into subvariants or subcategories. So when we think about an industry or industrial microorganism, these organisms are not really a single species. It should be a particular variant of that species. Then only it has some that this organism will have a the specific ability to produce this product. One more thing is that these variants can be either natural or artificial. Some of these variants emerge naturally, but we can also artificially make these variants by genetic engineering, protoplast fusion, like techniques, or gene editing, artificial recombination, site-directed mutagenesis. Using such technique, we can make the microorganisms newer strains of microorganisms. That's why we had a discussion. We have the whole people are debating whether the coronavirus is made by Chinese scientists or not. For industrial purpose, we can actually engineer an organism like synthetic biology. we can engineer an organism to have additional features or better productivity, etc. So these strains can be natural or artificial. So the point is, when we talk about the industrial strains, these are not just the species, particular species, it's a variety within a species. Maybe that variety is the reason for the particular flavor, especially for if it is a winery, they are making special type of wine. This flavor of particular wine is because of the particular variety of microorganisms they are using. Maybe it is specific for that only that industry. Maybe that brand is making such type of wine just because of they having a particular variety of Saccharomyces cerevisiae. So when we think about industrial strains, definitely they are way much different than the laboratory strains. So first let us discuss what are the ideal features of a industrial strain. So I am listing few of the ideal features, ideal characteristics of industrial strains. First one is stability. Unlike the laboratory strains or the natural wild strains, the industrial strain should be stable. Stable in the sense it should have stable growth rate, stable productivity, stable yield. So it should be reproducible basically. The industrial process should be reproducible. The one, if you make a product today, the same process can be reproduced tomorrow also. The strain should be stable in its growth characteristics, in production characteristics, and in terms of genetic characteristics. It should be stable. It should be reproducible. Second thing is growth rate, duration, and productivity. In every industry, they will count time as money. If it requires more time, definitely it will cost more. So, for an industrial strain, the growth rate should be maximum. It should grow faster so that the product will be produced very quickly. Second thing, the duration of fermentation should be minimal. So, we need the maximum growth rate in minimum time. Plus, it should have maximum productivity. The yield should be maximum. So, that's an industrial point of view. An ideal industrial strain should have maximum growth rate. The fermentation should occur in minimum duration and the productivity should be maximum. So, the organism which has the maximum productivity will be selected as an industrial strain. Next thing is nutritional characteristics and optimum temperature. In laboratory, we are growing microorganism in purified or refined media. We put NaCl, peptone, beef extract, and distilled water. We are using refined chemicals. But in industry, most of the industrial media are originated from the byproducts of other industry, like molasses. That's a waste product of sugar industry, or the sulfate waste liquor. That's a waste product of paper industry. This byproducts, the waste product, is used as a raw material for this bioprocess industry. So the organism should grow in cheap and easily available carbon source, maybe the medium, raw materials. So it should be resistant to the contamination and it should be able to break down the compounds in this waste material. Another thing is optimum temperature. The word fermentation itself means fever. So when the fermentation occurs, the temperature will rise. So the temperature will goes like 40 to 60 degrees Celsius. For an ideal industrial strain, its optimal growing temperature should be between 40 to 60 degrees Celsius, maybe even more. The reason is that if the organism has an optimal temperature of 50, when the organism grow, the temperature rises. If the organism's optimum temperature is 50, it will be happy during the fermentation. Its optimum temperature will be maintained throughout the fermentation because of the exothermic nature of fermentation. Suppose if an organism its with optimum temperature is 20 from the beginning, during the initial stages of fermentation, the temperature will be around 20-25, the room temperature. As the fermentation progresses, the temperature rises. The metabolism itself is an exothermic reaction. So during the fermentation, the temperature will rise and it goes to 50-60 degrees Celsius. So what happens? The organism will get inhibited because its optimum temperature is 20. So what we need to do? We need to cool down the medium to maintain the optimum growth temperature of the organism. The cooling the medium is an additional cost. So if the optimum temperature of an organism is come around 40 to 60 degrees Celsius, the cooling cost can be avoided. So for an ideal industrial strain, it should use cheap and easily available carbon source and the raw materials, plus its optimum temperature should be between 40 to 60 degrees Celsius. Next point is suitability for the process and equipment. In the previous chapter, we learned about different types of process, like batch culture, fed batch culture, continuous culture. So the organism that we are using should be suitable for the process we are intended to use it. If you want to run the fermentation as a continuous process, the organism should be suitable for that. The organism's growth characteristics should match the requirements of the process. Next thing is suitability for the equipments. Some of the microorganisms are known to react with the equipments. The most of the bioprocess equipments are made with either glass and most commonly stainless steel. Maybe to degrade the steel, very few of them, few microorganisms are able to degrade the steel. But most importantly, some of them are stick to the surface of the steel and form films. That is not recommended. It will be difficult to cleaning, and it will be difficult for kill or microorganism during the sterilization process. So it should not. An ideal microorganism should not react with the equipments. Next thing is feasibility of genetic modification. Most of the microorganisms in the industry are genetically modified in one way or another. So if the organism, the industrial organism is easy to manipulate genetically, it's better. So if the organism is a prokaryote, it's easy to manipulate. As the complexity of the organism increases, the difficulty of genetic manipulation also increases. And some of the organisms are well studied, like Escherichia coli. It is the most studied life form on Earth. So Escherichia coli is very easy to manipulate. Saccharomyces cerevisiae is easy to manipulate. But if you have a novel organism whose genetic characteristics are not known, it will be difficult to manipulate. So an ideal industrial strain should be easy to is the genetic manipulation in an ideal industrial strain should be easy. Next thing is byproduct and product recovery. Most of the microorganisms, they used to produce byproducts. Other than the main products, there are some byproducts. If a microorganism is producing a byproduct which is similar to the main product, it will produce complications during the downstream processing, during the isolation and purification. We need to add another step to avoid the byproduct from the main product. So ideally, the industrial strain should not produce byproduct, and it should be easy for the downstream processing. The product recovery should be easy when we are using an industrial strain for the bioprocess. Next thing is toxicity of product or organism. Product of the organism and the organism itself should not be toxic. If it is toxic or pathogenic, the industrial workers will be at risk. So an ideal organism should not produce any toxic products, and the organism should not be pathogenic. Like if an organism is producing an excellent product, but if the organism is causing another disease, it will be a risk factor. So the industrial people may get affected, the environment may be get affected, the neighboring peoples may be get infected. So an ideal organism should not be pathogenic. If we are making a product using Salmonella typhi, there's a risk the typhi should maybe leak from the fermenter and it cause disease to neighboring population. So these are the ideal characters of industrial strains. Let me summarize this one. An industrial strain ideally should be stable. The growth characteristics, production characteristics, everything should be stable. It should be reproducible. Secondly, an industrial strain should have maximum growth rate. Duration of fermentation should be minimal, and productivity should be maximum. And the ideal industrial strain should grow in cheap and easily available raw materials, and the optimum temperature should be between 40 to 60 degrees Celsius to avoid additional cooling cost. And the industrial strain should be suitable for the process we are intended to use, and it should not react with the equipments. And it should be feasibility of genetic modification should be there so that we can modify the organism for our use. and should not produce byproducts, and the product recovery should be easy. And finally, the product or the organism should not be toxic or pathogenic. So, in the nature, it is very difficult to find an organism which has all these characters. We listed many characteristics. So, in nature, it is difficult to find them. So, what we are doing, we isolate an organism, a wild type microorganism from the nature, and we will use several techniques like genetic manipulations, selection, screening, and everything to make this wild organism to an industrial organism. So we can convert a wild strain into a industrial strain using a variety of strategies. So at the end of the day, we'll have the wild strains and industrial strains. And this table shows the main difference between a wild strain and industrial strain. If you look at the details, for the wild strain, the reproducibility is poor in terms of growth rate, product formation rate, and titer. Titer is the yield actually. When come to the industrial strain, the reproducibility is high. Reproducibility is basically what the stability of the organism. It's more stable, it's more reproducible. Secondly, the wild strains are susceptible to product inhibition. But in case of industrial strain, they are highly tolerant to product inhibition. You must have heard about the feedback inhibition and feedback repression. The industrial strains are basically immune to that type of inhibitions, so that the product formation will be high, yield will be high. For wild strain, genetic stability is poor, but the industrial strain, genetic stability is high. Then the wild strains are able to use variety of substrate, but the industrial strains are acclimatized to use cheaper and wild variety of substance. And finally, for the wild strain, the poor substrate conversion rate, basically the product formation rate is poor in case of wild strains. For an industrial strain, very high substrate conversion rate. So we, after isolating a wild organism, we will use various strategies to improve its characteristics to make it as a industrial strain. So these are the steps in developing a industrial strain. So firstly, the first step is to isolate a microorganism from the nature or from other sources. Isolation of microorganism. Once we have the microorganism, we'll look for the product it is forming, whether it is forming a novel product or it is producing a interesting compound. So second step is screening, screening for new products basically. Then we look into the metabolites. Even if we get the product, we'll look into the entire metabolic pathway to confirm the product formation is novel and useful. And once we get the organism which produce a novel product with interesting metabolites, we go for the maintenance of microorganism, basically the preservation of microorganism. And finally, we go for strain improvement. We use various strategies to improve its characters, the characters of a wild strain to get the ideal industrial strains. In this unit, we are going to talk about the first four step, and the next unit we will be discussing strain improvement. So first step is to obtain a microorganism which is able to produce an interesting product. So how to get this microorganism? For getting an microorganism, we use screening methods. Screening methods are basically a set of procedures for the detection and isolation of organisms which possess potentially interesting industrial properties. We are looking to get an organism which produce some compounds, maybe some biotransformation or waste degradation, something like that. We can either use empirical methods or rational methods. Whatever method we are using, our aim is to find a microorganism or a group of microorganism which is having industrially interesting properties. For the screening, we can use two different methods. The first method is to obtain a microorganism from culture collections. Second one is to isolate microorganism from nature. That's what is really called screening. So first option is to get the microorganism from the culture collections. Culture collection is like a repository or library, or more like right now this is more like a Flipkart or Amazon. People's, the scientists basically, who found a microorganism with potentially interesting characters, they will deposit this microorganism in this culture collections, and their patent rights will be protected there. And if some industrial person is interested in that microorganism, they can just purchase it from the repository. That type of centers are called the culture collections. In world, we have many culture collection centers. The most famous one is ATCC, American type culture collections. It's based on USA. Then we have NCIB. Then in India, we have MTCC. All these are culture collections. They have the different cultures of microorganisms. Like they have microorganisms, they have plant cells, animal cells. They preserve these cells in the culture collections. If somebody wants it, they can just purchase it. If you want to get an organism which is able to convert one compound to another, you can search in these culture collections to find it. Or if you want to start a winery, you need Saccharomyces cerevisiae, the best variety of Saccharomyces cerevisiae. You can search in the culture collections to get the available options. I will show you how these culture collections work. So just go to Google and type ATCC, which is the most famous culture collections. The first one shown here is their homepage. Go to ATCC homepage. So this is the culture collection center. They have different types of cultures. They have bacteria, they have fungus, cell lines, plant cell, animal cells, everything they have. If you want Saccharomyces cerevisiae, just go to the search and give a search for Saccharomyces cerevisiae. So just like our Flipkart and Amazon, they are listing everything with the price. There are some few of their details are given here, some specifications. If you really want to know more about this microorganism, just click on it. So once we click there, we'll go to the more specification of the organism, who made it, how, what are the properties, what are the description regarding this organism. So culturing methods are given, history, documentation. So then if you like the organism, just given the quantity and add to cart. So this is how the culture collections work, just like an online shopping. You can give your address and they will deliver in the doorstep. The getting the microorganism from the culture collections has both advantages and disadvantages. The main plus point of this method is that it is the easiest method. You just go to the different culture collections, look for the specifications, and purchase the best one. The downside is that nobody is going to put the best microorganism in the culture collections. If someone found a microorganism which is producing a novel antibiotic, he is not going to put it in the culture collections. He will sell it to an industry, or he will start an industry by himself. So the best microorganisms cannot be found in the culture collections. It's possible maybe someone did that, but it's very rare. To get the best microorganism or novel characters or novel antibiotics, culture collection is not a good option. Then we have the second method, isolating the microorganism from the nature. That's basically called screening. Screening basically search in the natural resources for novel microorganisms. We know microorganisms are everywhere. It is in the water, it's in the soil, it is in us, in the laptops, in the mobile phones, everywhere. It is spread everywhere in this world. And its diversity is it's very much diverse. We only know about 2% of microbial population in this whole world. 98% is unknown. They are producing many different types of antibiotics. They may be producing unknown types of pharmaceuticals, drugs for every possible disease. But it's very difficult to isolate them. Most of them are unculturable. You cannot culture it in the laboratory. But still, if you really search for the microorganism, its chances are there you will find a microorganism which will have interesting industrial properties. Maybe it has a novel property. no other organism in this world have ever reported of. So that method of finding a microorganism with industrially useful properties is called screening. Basically, screening works from the natural sources, maybe the water from a particular river or from the soil from a particular place. We'll go take this soil and look into the microbial populations and look into the product what they are forming, the metabolic that they are forming. That process is called screening. Screening is basically a search for industrially useful microorganism in natural sources. When compared to the cultural collection methods, it is way much more tedious. For getting a microorganism from the cultural collections is like maybe take 1 week. You don't have to do anything, just go to the cultural collections, find the microorganism, just order it. They will deliver it in the doorstep. But getting a microorganism from the nature, the industrially really useful microorganism from the nature, will take something from 2 years to 10 or 20 years. But the advantage is that there is a possibility that you will find the best microorganism or the microorganism nobody ever heard of. Maybe a microorganism which produces an antibiotic which is so novel that it can be used for a variety of diseases. Suppose you found a microorganism which is producing a drug which kill coronavirus. That will be a breakthrough. So such type of microorganism can be found from screening. And there are two different stages of screening. If you are going for the screening, there are two different stages: the primary screening and the secondary screening. In the primary screening, the basic idea is that it's for the detection and isolation of microorganisms which have potentially interesting industrial applications. Which means in the primary screening, we are looking only into one feature, whether the microorganism is producing a compound. If you are screening for antibiotic producers, the only question in the primary screening is that whether the organism is producing an antibiotic. If yes, we will go for we'll isolate the microorganism and go for the secondary screening. On the primary screening, we are looking into the whether the organism has any interesting industrial applications. In the secondary screening is the detailed evaluation of real value for the industrial process. In the beginning of this presentation, I talked about ideal characters. So whether the strain is stable, whether the compound is novel, what is the nutritional requirement of the organism, what are the whether it is reacting with the equipments, everything will be evaluated in the secondary phase. So if an organism if I am going to screen for antibiotic producers in the primary screening, I will take the soil samples or the water samples. I isolate the microorganism and I look into what are the organisms which are producing antibiotic. That's only criteria in the primary screening. The microorganism which are producing antibiotic, I take it for the secondary screening. In the secondary screening, I look into the details. Whether the microorganism is producing a novel antibiotic or an existing antibiotic. Whether the organism is stable. Whether the what are the identity of the organism, what are the species, what are the genus, everything. Whether it is reacting with the equipment. Whether it produces any byproducts. Everything, the real industrial value, the ideal characters of the organism will be evaluated in the secondary screening. So the screening is basically the evaluation of or the isolation of the organism from the nature for industrial use. It has two different stages: primary screening and secondary screening. We will discuss the more details of the screening in the next presentation. Thank you so much.